We are now going to utilize all of our knowledge from making equivalents and the mole to doing mole conversions. As a little review, let's discuss dimensional analysis because all of this math is dimensional analysis. We're just creating new equivalents. But from previously, no matter what chemical formula I give you, so in this case, the chemical formula for ibuprofen is C13H18O2. How many atoms of hydrogen are in the sample of ibuprofen that contains 26 atoms of carbon? So I only really need to focus on carbon and hydrogen. So if I have one molecule of C13H18O2, there are 13 atoms of carbon for every 118 atoms of hydrogen. If it asked us for oxygen, I would add that on because then it would be 2 atoms of oxygen. Start with what's given. And then once you have given, you can solve for what you want. So I have 26 atoms of carbon, but I want atoms of hydrogen. In order to do that, I have to make sure my units will cancel. And so the numbers I put here are going to be my equivalents. So the 13 is going to go here, 18 is going to go here. My atoms of carbon cancel, my atoms of hydrogen remain, and I get 36 atoms of hydrogen. So very easy and straightforward. The next steps is what happens if our equivalents change. Reviewing the mole triangle, remember that this is another way of doing equivalents where everything relates back to the mole. If I was to convert from moles to representative particles, remember that representative particles could be formula units, atoms, molecules, ions, etc. It really just depends on the question itself. So if I need to go back and forth, you can definitely go between moles and representative particles. You can also go between moles and molecular weight, such as grams per mole of the compound. And if it's a gas, you can go between liters and the mole. But using this triangle, we can save a little bit of time and effort by going between them instead of having to convert everything back into the mole. And I'll show you 2 ways to do this. But because we know these are all equivalent to each other, we can say 6.02 times 10 to the 23rd representative particles also is equivalent to 22.4 liters. Vice versa, if you do, representative particles to grams per moles or liters to grams. So all of these can be utilized in that mole triangle. So I'll show you. How many moles are in 3.54 times 10 to the 24th formula units of sodium chloride? Now, in the bottom of this slide, they have all of the conversions from that triangle simplified in the way that we learned dimensional analysis. What I like to do is highlight what's given and what we want so I can see what conversions we need, and that way I can ignore what we don't need. So how many moles? I believe we're going to need to know moles, and they give us formula units. It's important for us to know formula units is one of those terms that goes under representative particles. So I only need those, and I don't need to worry about the rest of it. Start with what you're given. And this is NaCl, that's why I know it's formula units and not molecules. And you want one on top, given on the bottom. So I want moles wrong number, 6.02 times 10 to the 23rd So that's where these are coming from. When I plug that into my calculator, I get 5.88 moles of NaCl. Go ahead and plug that in and check and see if that number is correct. In example 2a, it asks how many formula units are in 6.5 moles of silver 1 sulfate. Before I even start with the problem, I like to just make it a habit of knowing what is this compound. We need to remember that the Roman numeral tells us the charge. So if I have silver 1 plus, and I have to remember that sulfate is SO4 2 minus. This requires that crisscross, and so silver sulfate is going to be Ag2SO4. I may or may not need this for this problem, but it's good to always be able to do that. Now, it's giving us moles, and it's asking for formula units, which falls under representative particles. So formula units is the smallest version of this ionic compound, and so I just need to do a one-step conversion. So I'm going to come down here, and I'm going to highlight the two equivalents that matter for this specific problem, is mole to representative particles. I don't need grams because I didn't mention grams in the problem, or liters, so I can ignore the rest of it and focus on just what I highlighted. Alright, so always start with what you're given, 6.5 moles of silver sulfate. I'm going to use dimensional analysis, and on the top I'm going to put what I want. So instead of me putting representative particles, I can actually interchange that with formula units. So 6.02 times 10 to the 23rd formula units of silver sulfate, and then divided by 1 mole. That is the conversion. If you plug in a number times a very large number, it should end up being a very large number. And so if you did this in your calculator incorrectly, that could kind of tell us, okay, let's go back and check, but you should be getting a larger number. And I got 3.91 times 10 to the 24 formula units. Example 2b is very similar to example 2a, but let's really look into it. How many atoms of oxygen are in 6.5 moles of silver sulfate? So on the previous problem, we found that silver sulfate looks like this. I cannot assume that atoms is going to be the same thing as the representative particles, because silver sulfate is an ionic compound, and the smallest representative particle for this entire compound is going to be a formula unit. I can't do atoms because it's a compound, and if I want to really focus in on specifically oxygen, I'm going to have to do an additional conversion. So if I have 1 molecule of silver sulfate, how many atoms of oxygen? It has everything to do with that subscript that's following. And so for every 1 molecule of silver sulfate, I will have 4 atoms of oxygen. It's also still very important for us to use the conversions or equivalents correctly. So I still need to convert it to formula units for the representative particles, and then I could add that additional step, but I can't skip that conversion into the formula units. Okay, so if I have 6.5 moles of silver sulfate, and I'm going to have to get it into formula units first before I can figure out the atoms. I have to find that little medium point. So 6.02 times 10 to the 23rd. I'm going to do F dot U for formula units. And that way those moles cancel. And then next step, I have to do my new equivalent. So 4 atoms. And instead of doing molecule, you can also change this to formula units. And those units will cancel, and I'm going to be left with atoms of oxygen. It's important to note that this additional step is only required when you have to go beyond the smallest representative particle. But that's why it's going to be very important for us to identify what is the smallest representative particle so we can still answer these types of questions. All right, so just to review what I was just hitting on, particles can be tricky. So we need to use Avogadro's number always to find the representative particles. Even if I have to do that extra step, we still need to figure out what are the representative particles, whether that be ions or atoms, if it's a pure, element, or compounds or molecules. So we need to find the representative particles first, and then if we have to go and do one additional step, we can, but we can't forget that first step. What exactly is the representative particle for the substance in the problem? So in the previous problem with silver sulfate, it's a metal plus a nonmetal. So that's an ionic compound, and that's why it is a formula unit. But if I was to have, let's say, CO2, that is a covalent molecular compound, and so that would be a molecule. So we need to be able to identify, based on what we throw at you, what type of representative particle it is. If it was a metal, let's say I just had nickel by itself, then it'd be okay if it's an atom, and then the representative particle would be both atoms, and if you needed to find atoms, that's the setup for that. So that's going to be the tricky part there, is being able to identify what is the smallest based on the compound itself. Were you asked to find the representative particle? If not, tack on one more conversion factor to go from representative particles to atoms based on. So in example 2a, we were asked to find the representative particle. On example 2b, we were asked to go one step further because it asked for something that was not the representative particle. So we're going to have to be able to look at these questions and figure out exactly what is it asking. Here's a little tip or trick. This is for if you have to go past the representative particle. Like on example 2b, we kind of did this conversion. If I had one representative particle, that could be formula unit, that could be molecule. So one representative particle is equal to the subscript of the particle. So previously, if I had Ag2SO4 and I wanted to focus on the oxygen, that's why we came up with this one formula unit of Ag2SO4 is equal to 4 atoms of oxygen. So that is the exact equivalent that we came up with. So this is a very helpful broad umbrella term for how we can do that in future problems. Example 3. If a solid gold ring weighs 2.1 grams, how many atoms of gold are in it? So first, if I have a solid gold ring, what is the only element there in this gold ring? It's just going to be gold. This is not a compound. This is not an ionic compound, molecular compound. It's not an ion. It is a pure element. So if it's asking for atoms and it's a pure one element type thing, that is the representative particle. So I don't need to do an additional step just because it's asking for atoms, and that's because of it's only having one element in there. It's giving us grams. So it's going to be important to note that we now need the molecular weight of gold. So I'm going to highlight the molecular mass because they have using grams, and then ask for atoms, which is, in this case, the representative particles. So the two equivalent points that I will need are the representative particles and the molecular weight. But I need to go to the periodic table of elements and find the molecular weight of silver. I'm sorry, this is gold. So Au is 196.967. It's important not to round these numbers. You want to keep these numbers as is until the very, very end, and then you are welcome to round based on the significant figures of the problem. But you never want to round molecular weights. We are starting with 2.1 grams of gold, and in order to get to atoms, I need to have what I want on top, which in this case is the represented particles, 6.02 times 10 to the 23rd. That's going to be atoms per mole. And then for molecular weight, I can put that 196.967, and that's grams per mole. I want to keep those moles in there because the moles will eventually cancel. There are two ways we can do this problem. I'll show you the second way, but this is just the more straightforward way. You put what you're looking for in the top. You put what you're what you're looking for in the top, and then what you already have in the bottom. When I complete this math, I get 6.42 times 10 to the 21 atoms of gold. It should be a very big number because there are a lot of atoms in a certain amount of grams of substance. So the units cancel. Let me just take out those units, and then you should be left with atoms of gold. Now, I'll show you how the other way also works, but this is the more efficient way of doing it. Just erase this real quick. Going back to the mole triangle, you can always get everything to go back into moles. So if I was to get everything into moles, I can divide by the molecular weight. And that way those grams cancel. And then I can multiply by the representative particle. And the moles will cancel. And that's essentially, it's the exact same problem I had before, but I was able to skip the step, and we can kind of take out this middleman of having the mole divided by the mole and have them cancel out. So this is why it's going to be very important to use these equivalents to help save you time. But if you type this into your calculator, you get the same answer. Example 4. How many moles of helium are in a balloon that has a volume of 3.1 liters? So looking at this problem, I am now seeing liters, so I'll have to use this equivalent in there somewhere, and then it's asking for moles, so I can come back to using these equivalents. Helium is just going to be He by itself. So if it did ask for atoms, it would be the same thing. That's the lowest or smallest representative particle. But in this case, we can kind of skip it. I'm starting with 3.1 liters of helium. And I want what I want on top and what I'm given on the bottom. So I will put 1 mole of He on top and 22.4 liters. That's the number I get down here on the bottom. That way these liters will cancel, and I'm left with 0.138 moles of He. So this problem could be complicated, but since I know these equivalents, it's not so bad. Let's continue on. Bobcat wants to inflate a balloon by stealing dry ice. So dry ice is just CO2 in solid form. They put it under lots of pressure and very cold temperatures, and they're able to get gaseous CO2 into a solid form. So inside of it, and letting the dry ice sublimate. So sublimate means instantly go from a solid to a gas. This happens when you take dry ice out of a very cold environment and putting it into room temperature. So it'll instantly turn into a gas, and that's why it's so much fun to play with dry ice and put it out on the surface and see what happens. If he wants the balloon to have a volume of 4.2 liters, how many grams of dry ice should he weigh out? So this question seems a little confusing because it's not saying we're given this. It's not saying I have this. It's asking us to figure something out. But because there's a number in there, we are going to still assume that that is the given. So 4.2 liters is the given. And it's asking for grams. So I'm going to go down here to our equivalents and highlight what it wants. So it has a liter in there, so I know this is going to be one of our equivalents. And then it's asking for grams. So I need to figure out the molecular weight of CO2. To do that, carbon is 12.01 plus, and then oxygen is 16. So the molecular weight is going to be 44.01 grams per mole. That's going to be all. If ever you need to figure out grams and they do not provide you the molecular weight, that's going to be the first step you do, is figuring out the molecular weight of the compound. So we have that now, and we can start the problem. I have 4.2 liters of CO2, and I want grams on top. So I'm going to put the 44.01, and that's grams per mole of CO2 on top. And then on the bottom, I'll put those liters. That's 22.4, and that's liters also per mole of CO2. The moles will cancel, and then my liters will also cancel, and I'll be left with grams. It is okay to leave out this portion. If you don't want to have those in, that's fine. The units will also cancel. So if you just left it grams divided by liters, you would also get the right answer, so don't worry. This would give 8.25 grams of CO2. So in order for us to get a specific volume of 4.2 liters of CO2, I would have to try to weigh out 8.25 grams of solid CO2 to get this to work. So this is a fun way of wording a problem where it's not really changing from previous examples. They just added some more wording in there to try to maybe like trip us off or just make us really think about what's going on, but we can still accomplish the right answer. Example 5b. So it's very similar to the previous problem because it's still talking about carbon dioxide. If the balloon filled with carbon dioxide has a volume of 4.2 liters, how many molecules of carbon dioxide will be inside? So CO2. Is this a molecular compound or a covalent compound? I use those words interchangeably. They're the same thing. Molecular, covalent, it's all nonmetals. An answer is yes. If this was ionic, the smallest represented particle would be a formula unit, but since this is a molecular or covalent compound, then molecules would be the smallest represented particle. So I don't have to do an additional step here. I can just assume that the represented particles are just going to be molecules. So let me highlight the two that we need. So it's giving us liters, and it's asking for molecules or represented particles. So start with what I'm given, and then on the top, I'm going to put those representative particles. Now, once again, you can leave it as, let's say, molecules per mole, or if you would prefer to just leave it as molecules, you would also get the right answer. See, if I left out the moles, it wouldn't really matter because the liters will still cancel and I will be left with molecules. When I do that, I get 1.13 times 10 to the 23rd molecules of CO2. If it asked us for atoms of oxygen, which it might in the next slide, we would have to do an additional step. But since we know that molecules is the smallest represented particle, I don't have to do that extra step. All right, here is where it asks us for that extra step. If the balloon filled with carbon dioxide has that volume of 4.2, how many atoms of oxygen will be inside? So we have to be able to recognize that the smallest represented particle for CO2 is molecules. And I still need to incorporate that step because if I need to figure out atoms, I need a represented particle in there first. But I needed an additional equivalent here. So if I have one molecule of CO2, how many atoms of oxygen? And that's that subscript. So I have 2 atoms of oxygen. So the way that we'd set this one up is very similar to the previous slide. And I have to add that additional equivalent in there. All right, so I got 2.26 times 10 to the 23rd atoms of oxygen. Example 6. This one asks how many atoms of oxygen are in 32.5 grams of potassium permanganate. So we need to be able to create what is potassium permanganate. So potassium is a +1 charge because it's in column 1. It's a column 1 metal. And permanganate is MnO4, and it has a -1. Because they cancel each other out, then the answer is KMnO4. And it's asking for atoms of oxygen. So if I look at this ionic compound, the smallest representative particle here will not be atoms of oxygen. Unfortunately, it'll be formula units. So if I was to use this, it would have to be formula units, and then I would have to do that additional equivalent. So if I had one, let me do a different color. If I have one formula unit of KMnO4, I would have 4 atoms of oxygen because of that subscript. So I need that additional equivalent. It's giving us grams, so I will also need to figure out the molecular weight of potassium permanganate. To do that, you need the periodic table of elements, and then so these are the 2 that I will need. So potassium, if I was to calculate that, potassium is 39.0983, manganese 54.938, and then there are 4 oxygens. So the molecular or molar mass is equal to 158.0363 grams per mole. That is necessary to answer this problem. 32.5 grams of KMnO4. And then I want what I want on top, so that would be the representative particles for potassium permanganate. And I want the molecular weight on the bottom, so molar mass. And if I left this problem here, I would be having formula units of potassium permanganate, but it's asking for atoms of oxygen. So I need that extra step, and I want to make sure those units will cancel, and I'm left with atoms. So I'm going to plug everything in. I got 4.95 times 10 to the 23 atoms of oxygen. So don't forget that additional step if it's not the smallest formula unit or representative particle.